Today, we're diving into what might just be one of the most beautiful and honestly powerful equations in all of physics. Because back in 1928, this single line of math didn't just solve a huge problem, it actually predicted a whole other side to our universe. A discovery that changed everything. I mean, really think about that question. Does that not sound like something straight out of science fiction? The idea that pure math, just symbols on a page, could tell us about a new kind of matter that no experiment, nobody had ever even dreamed of? Well, that's the incredible story we're getting into today. So here's our roadmap. We're going to start with the big physics puzzle that set the stage, then check out Dirac's brilliant solution. From there, we'll explore its absolutely shocking prediction, look at some of its other forms, and finally just soak in its amazing legacy. All right, let's set the scene. The 1920s, man, what a wild time for physics. You had these two revolutionary theories turning everything upside down. But there's one massive problem. They just could not get along. So on one side, you had quantum mechanics. It was absolutely amazing for describing the super weird world of tiny particles like electrons. And on the other side, you had Einstein's special relativity, which was perfect for anything moving close to the speed of light. See the problem? Electrons can move incredibly fast, but quantum mechanics just fell apart at those speeds. Physics was stuck. It needed a theory that could handle both worlds at once. And this is where our hero, the brilliant and famously quiet physicist P.A.M. Dirac, steps onto the stage. In 1928, he decided he was going to be the one to build that bridge. And he absolutely nailed it. He came up with what we now call the Dirac Equation. Its whole purpose was to create one single, elegant framework to describe an electron, taking into account both its quantum weirdness and the effects of special relativity. It was, and is, a total masterpiece. And there it is. Now, I know, it might look a little intimidating, but don't worry, we're not going to quiz you on it. The important thing here isn't solving it, it's what it represents. This one little line is a beautiful marriage between quantum mechanics and special relativity, the two biggest ideas in physics at the time. You can literally see the two worlds coming together right inside the equation. That psi symbol, that's the wave function, which is pure quantum mechanics. But look what it's mixed with. You've got m for mass, c for the speed of light, and space-time coordinates. All of that is straight out of Einstein's relativity. It's the perfect hybrid. Okay, but this is where the story takes a wild turn. Dirac was just trying to describe the electron, right? But when he actually solved his own equation, the math gave him an answer that he was not expecting at all. The math worked beautifully, almost too beautifully. It actually had two sets of solutions. One of them, it described the good old negatively charged electron everyone knew. But that second solution, well, it seemed to be describing something else entirely, something nobody had ever seen. Antimatter, the math itself was screaming that there had to be a mirror image version of the electron out there. The equation demanded, it required the existence of an anti-electron, a particle with the exact same mass, but with a positive charge instead of a negative one. Now, at the time, this was just a ghost in the machine, a purely theoretical idea. But get this, just a few years later, this particle, the positron, was actually discovered in experiments, proving Dirac's math had been right all along. So, the antimatter prediction is the equation's most famous claim to fame, for sure. But the thinking that went into it also led to some other really fascinating ideas. Let's take a quick look. To try and make sense of that weird second solution, Dirac came up with this incredibly creative picture in his head. He started to imagine that the vacuum of space wasn't empty at all. This is Dirac's whole theory, and it's a wild ride. So picture the vacuum of space. But instead of being empty, it's a completely full sea of electrons with negative energy. Now, if you pump in enough energy, say from a gamma ray, you can knock one of those electrons out of the sea and into our world of positive energy. It becomes a regular electron. But what's left behind? A hole. And that hole, that absence of a negative charge, acts exactly like a particle with a positive charge. That hole was the positron. It's just brilliant. And the equation's usefulness just keeps going. It's like this incredibly versatile Swiss Army knife for physicists. You can rewrite it for different situations, even for the curved spacetime of general relativity. Plus, in quantum field theory, the whole concept of a Dirac field is absolutely essential for sorting out some really tricky paradoxes. So let's just pull back for a second and look at the big picture. What's the real lasting legacy of this incredible piece of mathematics? More than anything else, I think the Dirac equation is just this stunning proof of the power of mathematics. It showed us that if you follow the logic of a beautiful, consistent mathematical idea, it can lead you to discover profound physical truths about the universe, truths you weren't even looking for. And this quote just brings it all home. Dirac's goal was super practical. He just wanted to get the electron to play nice with relativity. But in doing that, he stumbled upon a fundamental truth about nature and basically doubled the number of particles we knew about, all with just a pen and some paper. It's incredible. And that really leaves us with a final mind-bending thought, doesn't it? If one equation from nearly a century ago could predict something as fundamental as antimatter, what other secrets about our cosmos are hiding right now inside the equations being worked on today, just waiting for us to finally understand what they're trying to tell us?